Greetings to all. I am Dimitris Aris. I am an associate professor of food biotechnology in the Department of Food Science and Nutrition in the University of the Aegean. Our department is located in Limnos Island in Greece. Lecture number 16 will talk about the technology of generating bio-based products, production of bio-based products from agri-food waste. This lecture is continuing lecture number 15, and it's provided from AGRIMA project, namely Agri-food Waste Management for Sustainable Bioeconomy through Higher Education, Curricula and Upskilling. AGRIMA project is an Erasmus Plus project under the KA 220 action, and specifically cooperations, partnerships in higher education. A few words about our AGRIMA project. Feel free to visit our website following the link below. AGRIMA aims to foster universities' capacity building for the green transition through innovative practices and higher education curricula updating in agri-food waste management for the circular bioeconomy. AGRIMA specifically addresses number 1, advancing pedagogical methods for industrial agri-food waste valorization based on business-academia synergies, but also integrating citizen science in bioeconomy-enhanced waste valorization as a means of civic engagement and environmental advocacy. Our strong alliance, our strong consortium, consisted by 5 partners, with the Polytechnic School of Porto from Portugal being the coordinator, and the University of Marseille, University of the Aegean, University of Novi Sad, AVIPE and Web2Learn being as partners. In order to understand how we could achieve producing bio-based products, we need first of all to remember the term of a really ancient art and practice, namely biotechnology. Biotechnology is the use of biological systems for the development or production of a value product. High added value products, added value products. And this is not something new, even though we would like to apply it nowadays to achieve something modern, meaning the transition from the today's linear model of production towards the circular model of production of circular economy and circular bioeconomy. Biotechnology, as I have already told you, is not new. It's an ancient art, an ancient profession. You may recall ancient Greeks producing wine, others producing bread, others yogurt, anything that has to do with fermentation and the use of microorganisms to transform a feedstock, a raw material, to a new product that didn't exist before. If we travel to today, we could also analyze the term of industrial biotechnology, which is the use of biological systems, microorganisms or their derivatives, such as the enzymes of the microorganisms, for the development or manufacture of industrially useful products. If we look around, we may find many of them. already being in our lives. Discussing about microorganisms or their functional biomolecules, we find three main categories. We find fungi, bacteria, and their enzymes are as their functional biomolecules. There are plenty of examples of the use of microorganisms towards the production of numerous bioproducts. For many years now, we are using fungi to produce citric acid, for an example, to produce biofuels, to produce medicines, pharmaceuticals, nutraceuticals. The same with bacteria. We use bacteria for the treatment of, let's say, municipal wastes nowadays in big cities, or probiotic products as capsules. We also use functional biomolecules, derivatives of the microorganisms, such as enzymes, for many years now, for, let's say, bread and cheese, as bread and cheese additives or enhancers, as enzymes in washing powder to heat lipids and dirt, and enzymes that may be used in the chemical factories for organic synthesis. In order for microorganisms to produce their products, the biomolecules, they need their food that we offer the term of substrate. Microorganisms grow on a wide variety of substrates, and they produce a wide variety of products. And this is a weapon in our arsenal to use and to apply in the new bioeconomy, circular bioeconomy model. The food for microorganisms, called substrate, is used and converted into a wide range of products. Above all, and as an easier substrate to be used, sugars could be widely used in industrial biotechnology to produce numerous products. Thus, in microbial fermentations, fermentation is a part of biotechnology and the process where we have three pillars. We have the pillar of the feedstock, the raw material, the biomass, the substrate, the carbon source, which is needed for the energy of microorganisms. We have the second pillar, which is the tool, the workhorse, the microorganism itself, which through fermentation leads to the third pillar, which is the product, the bioproduct, which we find useful in many applications. Major products as categorized could be biofuels, organic acids, single cell oil, single cell protein. So you may easily understand that we might be able to use, as referred to lecture 15, the previous lecture, biomass, carbon source as material, and not fossil fuels, use microorganisms and produce almost anything that we use in our lives, so as to substitute fossil fuels that we use nowadays and replace refineries with biorefineries under the certain flow chart and mode that you see before your very eyes in this screen, which is the technology towards the bio-based products. Well, you need, again, under the framework of the three pillars, you need your raw material, your feedstock. You need your biomass, which is an alternative and renewable source of energy. You need the process using the tool, which is the microorganism and called bioprocess, so as the final product to be produced after some additional modification that we are going to talk about some more steps in the next slides. Let's go now to the first pillar. The raw material, the feedstock, our biomass. We should ask some questions to ourselves so as to understand the leverage that we can pull and why it's good to use renewable alternative feedstock, namely biomass. Why should it be renewable? Easy to answer, compared to fossil fuels that it is said that they are running out. Which type of raw material should we use in this technology to have an end of the line, having the final bioproduct? How do we choose our feedstock, our raw material, our substrate? How and when to use sugars, and how we could include the term sustainability under this framework. If we go back about not many years, 200, 250, 300 years, before the Industrial Revolution, we could easily see that agriculture, fishing, and forestry at that time covered all needs of society, all needs of transportation, all needs of lighting and heating, and of all needs of products. We could use this as a guide and return to these principles by applying industrial biotechnology, circular bioeconomy, and specifically bio-based production, and close the loop by using renewable alternative crops and their residues, most importantly their residues, to meet our needs. Because today, compared to the times before the Industrial Revolution, we have higher energy demand per capita. Thus, we need intelligent solutions and, of course, more and more optimized performance and productivity so as to totally substitute fossil fuels used as raw material. It would be good to understand what's the availability of our raw material. If we look closely around us, we could see that the available feedstock to be used as the raw material, the microorganism being the tool through fermentation and then having the final product, is almost everywhere around us. Specifically, you may see at your slide, the available feedstock for such process is food crops. All right, we have some things to talk about this sector later on. Agricultural waste streams, really interesting. Dedicated crops, wood forestry, and the really interesting sector of waste streams. If we could discuss about the holistic use of this feedstock, imagine that we call it from now on biomass, hiding our carbon source for the microorganisms through microbial fermentations. So if we could use holistically biomass, we could not only produce food or feed, but we could also produce bioplastics, biofuels, biosurfactants, biopharmaceuticals, bionutraceuticals. The thing is, what part of the biomass we are using, and we're going to analyze this in a while. So we can holistically use our biomass, as we say here, to produce almost everything. Which is the biomass composition then that we have in abundance around us, as I have already warned you? Well, biomass includes two fractions, the useful one and the non-useful one. The non-useful one, unfortunately, is abundant and non-biodegradable, meaning that the microorganisms could not easily use this fraction to continue microbial fermentation and end up in a final high added value product, because the non-biodegradable fraction, called also lignin, is a complex polymer having an irregular structure, and it is hard, strong, strict, rigid by design, and cannot be easily struck by microorganisms so as to continue the fermentation process and end up in the final product. On the other hand, there is also a useful fraction, including hemicellulose and cellulose. Both of them are polymers chains. Cellulose includes carbon-6 sugars, hexose sugars, hemicellulose, carbon-6 or carbon-5 sugars, hexose and pentose sugars, which could be used by a variety of microorganisms to be fermented and end up in the final product. If we could go to the classification of biomass, we could see and listen to some generation of biomasses. And nowadays, you may hear about maybe up to fourth generation of biomass. So what's the generation of biomass? First generation of biomass. It's the same thing that we call food. And the second generation is the residues of food crops, wood, and forestry. A classic example. If you have the grapes that we eat, or either we produce wine from the grapes. The grapes themselves are our food. Either we eat it or drink it when it's being transformed with industrial fermentations, industrial biotechnology towards wine. So the grape itself, it's a first generation biomass. Whereas the stalks, what remains from the process of winemaking, let's say, the stalks, the leaves, or whatever is left behind as residue and not being the food itself, it is considered to be the second generation biomass. Here's the full layout of biomass generations and the traits and drawbacks. All right. So the first and the second and the third generation of biomass. The third one that I have never referred to previously, it's the cells of the microorganisms themselves. Let's go step by step to see the traits and the drawbacks of each one. First generation biomass, the wheat, let's say, or the grape itself, or a fruit itself, it's rich in simple and easily fermentable sugars, glucose, fructose, etc., and having all necessary nutrients to offer a heavenly environment for the fermentation process so as to produce our valuable bioproduct. But here we have a serious drawback. Imagine that we used first generation of biomass, which is readily available for food as feedstock to produce any kind of bioproducts, from bioplastics and biofuels to pharmaceuticals and nutraceuticals. If we would do that, we would directly compete with food production. The use of land and water for irrigation would be not in favor for feeding people, but for producing a bioproduct. This is considered to be nowadays unacceptable, as we face major problems in feeding the people around the world. Therefore, we need to look for alternative solutions. Second, biomass, which, as I have told you, is the residues, the remains of the food production chain, would be more attractive to support my argument. Second generation of biomass is composed of lignocellulosic biomass, harder to break down than first, but not impossible, because it includes cellulose, hemicellulose, besides lignin, the strict, rigid lignin. It is consisted by cellulose and hemicellulose. Many microorganisms possess in their genetic arsenal the enzymes to break down such kind of polymers and end up in simple sugars like the first generation of biomass and continue fermenting and producing. The main advantage of the second generation of biomass is that it is derived from agricultural wastes. The raw material, the feedstock, is something that is a waste, something that we used to throw away and not use as food. Sometimes we use it as feed for animals, but it would be better to use it as raw material in a biorefinery. And the third generation of biomass is that the microorganisms themselves may produce intracellularly within the cell microbial oils, proteins, carbohydrates, anything. And the major advantage of this is that we have not at all conflict with food and land use, whereas the second biomass has something to do with the land use as it's the waste of the first generation biomass. So if we were about to use second generation, let's say, biomass as feedstock towards microbial fermentations, how are we going to choose our feedstock? We should be aware then about three matters: about the biochemical composition of our raw material, the yield that it offers, and the sustainability of the whole process. We are fine talking about substituting completely fossil fuels and refineries with alternatively renewable biomass and biorefineries, but are we sustainable to support it? This is an argument that we should consider strongly. Choosing our feedstock, and specifically watching on the biochemical composition, some examples of abundant biomass around us. We are not talking about the food itself, corn, soy, or another product as cotton. We're talking about the corn cobs, the cotton stalks, and the soy stalks, which are considered to be a waste and not useful for anything. So, first of all, when you are in the first pillar of the raw material, you need to know the biochemical composition of your raw material so as to understand what kind of process you are going to need, what kind of microorganism you are going to need. Are all microorganisms capable of transforming, fermenting corn cobs towards something which possesses the certain amount of cellulose, hemicellulose, lignin, and other compounds? So we should treat differently corn cobs from cotton stalks and soy stalks, etc., 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 etc. The first thing that you do when you say that, okay, around there we have a problem, which is called the waste, you have to analyze its biochemical composition to try to find how to hit that structure, exactly hit that structure, and move on with the process. Moving on about choosing the right feedstock for our process is the yield of the process, meaning how many tons of biomass, our feedstock, we're receiving per hectare of land. And from each ton of biomass, how many tons of sugars we may produce when treating somehow biomass and trying the polymers and complex structures to be in monomers and sugars. And when going to the fermentation process, fermenting the sugars, how many tons of product we produce from 1 ton of sugar produced from 1 ton of biomass produced from 1 per hectare. If we would like to assess the sustainability around choosing our feedstock, sustainability of feedstock selection, we should consider many factors as seen in the certain flowchart. We should consider the ecological impacts, the soil quality, and what remains after our actions. The same with biodiversity. Most importantly, what's the use of drinking water in the process or uh, in the process of producing the first generation of biomass and subsequently the second generation biomass. What's the utilization of the resources? The arable land as hectares and the drinking water. And by using our process and applying our process, what are the greenhouse emissions for the energy for sugar extraction, the energy for harvesting, the energy for fermenting, the energy of downstream processing to end up to a refined final product, etc., etc. I mentioned the term downstream process. We have also the term upstream process, and we have also the term fermentation. All of them together create the fully integrated bioprocessing system. Let me use my pen, laser pointer. So here we are having our renewable resource, renewable raw material, alternative feedstock. It's not fossil fuel. It's second generation biomass from, let's say, wheat production, wheat flour production. This is the haystack, okay? And the normally and in most cases, and that's a kind of drawback, but it is what it is, our feedstock, it's not readily available towards the use of microorganisms, so as our feedstock is not readily available for fermentation and then going on. Between them, there is the upstream processing step, which prepares and needs to be done to prepare the feedstock for fermentation, as it is not readily available. If you would take feedstock of certain biochemical composition and lead it to a bioreactor to perform fermentations, in most of the cases, the microorganisms could not tolerate that and the process would not work, would be idle. So you need to first include the upstream processing step, and after that, having an easily biodegradable raw material to use the microorganisms with certain technology, with high yields, etc., 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 to produce your bioproduct. But this is not the end. I will give a classic example of biofuels, such as bioethanol. Let's say then that we have molasses as feedstock. Actually, our feedstock is sugarcane in Brazil, let's say. So our sugarcane is going towards the production of crystal sugar that we eat by upstream processing. From the upstream processes, we have as a side product, as a waste, molasses. Molasses then can be easily fermented by a microorganism in performing alcoholic fermentation to produce ethanol. The ethanol is inside the liquid medium of fermentation, but it's not the final product. We have in, let's say, 100 liters of liquid fermented broth, we have no more than 50 liters of bioethanol produced. This is not the end of the line. We need the bioethanol as a final product to offer it as biofuel. Thus, we need to perform the downstream processing to end up to bioethanol. An example, in the same example, the downstream processing would be an easy step of distillation, let's say, to separate water from ethanol. By terms of economy speaking, if we would like to produce bulk product, such as a biofuel, the 80% of the operational cost of the whole process would be spent on achieving higher yields in the upstream processing and the fermentation processing. If we were talking about the above example, with the use of, with the production of a pharmaceutical, a highly pure substance, the 80% of the operational cost would be spent on the purification of the compound, the biopharmaceutical. Let's move to analyze a little bit more the first step, which is the upstream processing. As mentioned before, the raw biomass cannot be directly introduced into a bioreactor without prior being processed. And that's what upstream processing is all about. The first generation of biomass, if we have to deal with breaking down of lignocellulosic structure and extract the fermentable sugars and starch, but mainly in first generation biomass, the fermentable sugars and starch are readily available. This kind of processing, it has been implemented for a long time now. And of course, as mentioned before, the first generation of biomass, it would not be good to be used as it's competing food, irrigation land, etc., etc. The lignocellulosic biomass was considered to be a waste, and up to some point, generally, it was used for heating industry and the production of energy. We could do more than that. Using second generation biomass as alternative raw material source. However, because we do not have readily available fermentable sugars there, it requires higher capital input. Regarding pretreatment then, thus, of biomass under the framework of upstream processing, we need to revisit traditional agri-food process to integrate lignocellulosic biomass. Pretreatment steps are needed for both first and second generation biomass, such as hydrolysis, depolymerization, etc. And of course, the extraction of biovaluable components such as lipids, proteins, nutrients, etc. Just like in conventional agri-food processing methods, we have some steps in upstream process so as to prepare, to pre-treat our feedstock, our raw material, our biomass towards fermentation processing, and then the final step of downstream processing and the final pure product. So in the upstream process, some steps could be adjusting the particle size and selecting the appropriate fractions of the biomass. Of course, messing up, disrupting the structural integrity of biomass so as to hit the complex polymer structure and break down polymeric compounds as starch, lignocellulose, etc. Then when we do the first steps, it's to recover the carbohydrate components which are readily fermentable and throw away the rest, and have, if required, additional conversion steps and purification. So, as a note, while the technological foundation is similar, it does not fully align with conventional agri-food processing methods. Let me offer you again a conventional agri-food processing, upstream processing method. We want to make wine. Well, grapes are not readily available in the winemaking industry. They are somewhere in the vineyard. So we need to harvest in the vineyard, to remove any dirt, leaves, etc., to remove the stalks, to press the grapes and to have the must, and then ferment and produce the wine. This is a classical example of upstream processing. I have mentioned to you some steps from vineyard, the plant, the vine, towards the product, the wine. In the same rationale, we meet upstream process in the bioprocesses of a biorefinery. It's similar, but it's not fully aligned with the conventional agro-food processing methods. More examples of upstream processes, not specifically in a biorefinery mode. Sugar as being the final product from sugar beets and sugar cane, starch-rich crops, plant-derived oils and proteins, olive oil, soybean oil. This is classic examples, agro-food examples of upstream processing. Lignocellulosic residues from starchy materials, lignocellulosic feedstock from paper pulp waste, going now into a more biorefinery mode as we're talking about wastes. Thus, ending with upstream process, it's an essential part of the overall process, as numerous technical parameters and strategic choices are involved. Comparable evaluation of the overall process design, and the near future, new findings every day will reveal optimal combinations of feedstock, processing routes, and end products. An example is having a certain feedstock with a certain biochemical composition. We use step 1, 2, 3, 4 in the upstream processing. Then we use a certain strain of microorganism which finds our raw material ideal as substrate, and then offering as bioprocess engineers the best performance and the best environment so as the strain of the microorganism to perform with high yields and productivity and produce high volumes of high added value products. The key metrics of the upstream processing include the energy demand per ton of biomass, the chemical input per sugar yield, and the enzyme efficiency and byproduct profile. All of this should be taken into consideration so as to see whether our processing is sustainable. Moving on to downstream processing, the key objectives of this step is to isolate the target compound from the complex fermentation broth. This is the target compound, the final result, the final product, the refined final product, which is hidden, let's say, in the fermentation broth. And we need to know the nature of the final product so as to fish it outside our fermentation broth. And of course, the second key objective of downstream processing is to achieve market-ready purity. It depends. Do you need a bulk biofuel product or a high purified biopharmaceutical medicine for human use? So we need to achieve market-ready purity, concentration, and packaging standards of our final product. The essential stages of the downstream process after the fermentation process is to break down the cells. If the product is intracellular inside the cell, then if yes or if not, some products are produced outside the cell. The cell produces and throw the product outside. Then, of course, the cell removal to have the liquid broth with the compound that we need, to concentrate it, to purify it, and then having the formulation to lead it to market, either business to business or business to people. The fermentation broth, fermentation is the stage between the upstream process and the downstream process. This broth is complex and unstable. As you may see in a biorefinery concept mode, we have many problems to address and to solve. One of them is the complex and unstable fermentation broth. It is not, unfortunately, it is not primarily composed of the compound that we need to have as an end product. It's primarily composed of water, but also cells, microbial cells, and intracellular and extracellular compounds that probably are not of our interest. It also contains residual, meaning unconsumed substrate and nutrients from the upstream processed raw material, buffer components, salts, antifoam agents that we use in the fermentation processing. And most of the times it presents only a tiny fraction of the desired product. Last but not least, we have also before us instability factors such as cell disruption, cell lysis, and then enzymes released in the broth, which may break down our product. So we may have risk of product degradation or reuptake by cells. So this is a complex, unstable, and always to monitor broth to move on. Optimizing process flow and output quality in general, the whole process meaning, the key evaluation criteria, the holistic process, the key evaluation criteria would be the efficiency and precision of the process, handling capacity from apparatus to human resources, energy requirements, throughput rate, output of our valuable product versus waste generation of the bioprocess itself, long-term viability and safety, and of course, economic viability, sustainability. Thus, the effective optimization of the holistic bioprocess, upstream processing, fermentation, and downstream processing, from feedstock to end product, the effective optimization requires synergy across all process units. I hope that you have found this lecture interesting, and it would be really important for our AGRIMA project that you take a minute to evaluate our lecture. This lecture is lecture number 17. You may scan the QR code that will lead you to the evaluation form, including all AGRIMA lectures, but you may also type the link that you see or use the PDF slides from our website to press the link and go to the evaluation form. Thank you for your attention, and I will see you in lecture number 18. Thank you very much.